So you'll jump from one node to another until you reach the point where your object is, where you want to access it. So it's kind of recursive procedure. And security properties of this scheme allow you, it's the first one that it's sound, which means that if I'm entitled to see something, I'll definitely be able to get access to that. And the second one is completeness, meaning that if I'm not entitled to see something, I won't be able to do that. And even it's probably secure even when someone can adaptively corrupt different nodes, different users, and so that we still show that it's impossible for them to get any additional information using any number of keys, any combination of them. So this is some example, a simple example how it works. And this graph is a little bit more complicated than a tree because you see there's edges coming to the same node. And here, if for example, say I'm at node 3, that I will be able to derive a key for node 4 using public information. And if I'm in node 1, I'll be able to get access to everything in the hierarchy. And on this graph, it's not clear, but all keys K1 through K4 are private, but everything else is public. So you'll be able to use that information, the labels and the information about the edges to derive keys of other nodes. So now I'd like to switch to the dynamic version of this scheme. And as already mentioned before, that throughout their operation, hierarchies are going to evolve. So there can be a number of changes that happen to them. For instance, addition or deletion of classes when we want to restructure the hierarchy, or we want to add new relationship between classes, add new edges, or remove some other edges, or if we simply just want to rekey a certain class because we know that the secret key for that particular class was leaked. The previous scheme is not going to support this very well, but if we just introduce small changes to the basic scheme, then we'll be able to support all of the required changes. And here, the only change that we need to introduce is to the private key, and this is pretty small change. It doesn't make it much more complicated. So as before, for each node we pick just one secret key, but this time, and it's picked at random. But this time, instead of calling this k, we'll call it k hat. And as before, this is going to be the secret key for each user. And if you want to have access to a certain node, you get that key hat that belongs to that particular node. But now, actually, the encryption key used in the hierarchy is different. It is derived from the secret key and from the label. So this is one additional step that we insert in between using one-way hash functions. We'll see how this will help us to make sure that all dynamic changes are locally contained in the graph. And the rest of the scheme remains unchanged. And next, I would like to show how changes are introduced in the graph. An insertion of an edge is easy. So everything you need to do is basically create a public label for that edge, and we're done. This will allow us to go from one node to follow that edge, basically derive necessary keys. But deletion of an edge is trickier. And first of all, we can just take that edge out. It's not a big deal. But the problem is, if someone stored that particular information, they still will be able to have access to the node, even though right now they're not supposed to have access to it anymore. So we need to do something else. And this is called X-member problem, when we want to make sure that people who used to have access to something don't have access to that anymore. And the description of what actually needs to be done maybe not very clear here, but the basic idea is that what you need to do, you take all children of the node affected and you change their labels. So this is public information only. Secret keys are not affected. And using and you regenerate all public information based that is computed based on those new labels. And in this case, since the public information changed and the keys changed, and in this case, people who used to have access, and if they're not able to derive it right now, they won't have access. So the X member problem is solved. The next thing that we need to look at is insertion of a node. And actually, insertion of a node or deletion of a node are easy given that we have basic operations for insertion or deletion of an edge. And so to insert a node, you basically create a new node and insert necessary edges that touch that node. And to delete a node, you first remove all edges that touch it one at a time, and then take the node out. So it's also pretty straightforward. And then the one last operation that we want to be able to do is key replacement. As already said, if we know that the key was compromised, we want to replace the key and rekey all users that belong to that particular class. And so to be able to do this, what we do, we create a new secret key. It's going to be a new random number. And then we compute the encryption key for that class, which is going to be hash function of the secret key and the label associated with that class. And since this key modified, we also update public information about incoming and outgoing edges for that node because they're a function of the secret key. And so with this, we actually locally contain those changes. We update only one node and edges, public information about the edges that touch it. And the difference here with key replacement, we change the secret key. But with the deletions, we actually change the labels. The secret key remains the same, and so the users are not affected. Their key stored on their end is not affected. And this is actually the novel part that hasn't been done before. And I would like to spend a couple of minutes talking about other models, other access models. So in this basic scheme, which is very natural, very straightforward, when you have access to everyone below you in the hierarchy, there might be situations when you need actually to enforce policy that works the other way around, so that I'm able to access something higher up in the hierarchy. For example, I'm a student at Purdue, and I'm entitled to see all documents stored at the level of the department. And then for me to be able to go up, there should be some sort of mechanism, like we need to reverse the mechanism that we use to be able to support this. And so this kind of inheritance is called downward inheritance. And to be able to do this with our scheme, the main thing that we need to do is to generate a reverse of the graph, of the access graph that we originally have. And so in the reverse graph, which we call GR, we reverse all edges. Basically, if there was an edge coming from a node A to node B in the original graph, we replace it with an edge going from node B to node A in the new graph. And then we run the same key assignment scheme. Everything remains the same, but right now it works the other way. And if you wanted to support both, then you'll have one key for the normal graph and another key for the reverse graph, and then you can have both